Hi guys, welcome to the second video, chapter 12, section 2, gravity. This is the second video that we'll be doing on our chapter on force. And to get us started, the very first question that was asked in your notes packet was, how are weight and mass related? Well, weight is equal to the mass of an object times its free fall acceleration. Here on Earth, objects accelerate at 9.8 meters per second squared. So, mass times free fall acceleration, and in parentheses beside that you can write 9.8 meters per second squared, because that is the acceleration that we have here on Earth. Weight is a measure of the gravitational force that is exerted on an object. Weight is equal to mass times free fall acceleration, and the way that you can write that is W equals m times, I put a little dot for times g, W equals m times g, and weight is measured in newtons, same as force. Weight is measured in newtons, and it's different from mass because mass is the measure of how much stuff is in something. Mass is how many atoms I make up, I am going to have the same amount of mass whether you take me here or you put me on any other planet. I'm still made of the same amount of stuff. That's my mass. We can measure that in grams or kilograms or pounds. And my weight is the gravitational force that an object experiences because of its mass. So here, I am 125 pounds, and I feel like I'm 125 pounds. What we can write for the example is that in kilograms, let's see here, probably right about there. In kilograms, my mass is 56.8 kilograms. This is me here on Earth. My weight is also 56.8 kilograms, but because we record weight in newtons, 56.8 times 9.8 meters per second squared would give me 557 newtons. So here on Earth, my weight in newtons is 557 newtons. And on the moon, my mass would stay the same. I would still be 56.8 kilograms on the moon because I'm still made of the same amount of stuff. So I'm made of the same amount of stuff here as I am on the moon, but because gravity pulls me down less, my weight is actually 1/6 of what it is here on Earth. So my weight would be 93 newtons. Is that what I wrote? Yep, 93 newtons is my weight. And that would feel like, so on the moon you feel lighter, even though you have the same amount of mass, if your weight feels lighter, it would feel like 9.5 kilograms. So while here on Earth, I feel like I weigh 125 pounds, on the moon, I would feel like I weighed 21 pounds. I would feel like 21 pounds was what my body was being pushed down to the ground with. And my mass would stay the same. Alright, going to set that one down. Now our next question is, let's see, is that about right? Yep. Why do objects fall to the ground when dropped? Now you already know the answer to this question. All objects in the universe attract each other through the force of gravity. So when something falls to the ground, it's because the Earth attracts that thing to it. And actually, as much as it doesn't seem like it, that thing also attracts Earth, but because the Earth is so much bigger, we don't see that. We don't see the Earth come up to meet you, we see you go down to meet the Earth. if you fall. Newton's law of universal gravitation, so that's the blank that you write in. Newton's law of universal gravitation gives the size of the gravitational force between two objects. Now we find that force by the gravitational constant times the fraction of the force of the first, or the mass of the first object, times the mass of the second object, divided by the distance between them squared. And that will give us how much force is between those two objects because of gravity. Where M1 and M2 are the masses of the two objects, d is the distance between them, and g is this gravitational constant for the equation. I'll give you a second to write that down. And I'll put that down. Now, all matter is affected by gravity, so two objects, whether they're big or little, whether they're these two markers, or me, or you, or your chair, Sally the salamander, the earth, the sun, the stars, anything, cars, any two objects always have a gravitational force between them. But the thing is, when something is very large, like the earth, that force is very easy to detect. Nobody wonders if we're attracted to the earth. We feel it every day when we walk down the hallway, when we get out of bed, when we jump, we fall down. So we know with the earth, because it's a very massive object, we can see that force very easily. The thing is, gravitational force increases as mass increases. So the gravitational force between these two markers is not strong at all, especially considering that the force of gravity from the earth is working so much more on them. Now, if we were to put these two markers out into space, where they were completely by themselves and close enough, they would be drawn together by gravity. But usually, there's bigger things around them that would counteract this gravity and make it not as noticeable to us. Which is why we have to observe gravity between really big things, like the moon and the earth and the sun, and the moon and the earth and the sun, and Mars and all the planets. So gravitational force also decreases as distance increases. The farther we are away from the sun, the less gravitational force the sun has on us. The farther we are away from the center of the Milky Way galaxy, the less gravitational force the center of the Milky Way galaxy has on us. So the closer we get, the stronger the force. Now, our next question is not this, but this. So, what is the relationship between free fall acceleration and mass? You should be on the section that says free fall in your notes. It's just below the picture of different objects and their gravitational force. So if you're just below the picture on the part that says free fall, you're in the right place. And what is the relationship between free fall acceleration and mass? So, in the absence of air resistance, all objects falling near Earth's surface accelerate at the same rate regardless of their mass. In the absence of air resistance, all objects falling near Earth's surface accelerate at the same rate regardless of their mass. Of course, you guys know the rate is 9.8 meters per second squared. Now, a free fall is the motion of a body when only the force of gravity is acting on it. So when there's only gravity acting on something, that's called free fall. Air resistance can balance weight. So what happens if you fall towards the Earth where we have an atmosphere surrounded with air is you'll finally reach a terminal velocity. Now the terminal velocity is a constant velocity of a falling object when the force of air resistance is equal to the magnitude and opposite in direction of the force of gravity. So while you accelerate at 9.8 meters per second squared, eventually you'll come to a point where you're at your terminal velocity. You're going so fast that you're not accelerating anymore, you've reached a constant velocity and air resistance is keeping you from accelerating any further. Our final question for this section of notes, yay, the final one, is why does a projectile follow a curved path? A projectile is something that is thrown. You can think of a cannonball, or you can think of throwing a ball, or you can think of something orbiting, something else. That's all projectile. So why does projectile motion follow a curved path? Well, it has two components, and I'll show you a picture so you can see the two components. It has horizontal and vertical. So when the two motions are combined, it has this nice curved path. You can see that in the green. So when horizontal and vertical are combined, we get this curved path. And the reason why it has both, projectile motion has a horizontal component because after you've thrown a ball, no horizontal forces are acting on the ball if air resistance is ignored. So the horizontal component of the velocity of the ball is constant after the ball leaves your hand. You've given it a velocity, and that part of it stays constant. Now, especially if you forget about air resistance. Now, it also has a vertical component, and I'm sure you guys can figure out what that comes from. When you throw a ball, gravity pulls it downward, which gives the ball vertical motion. In the absence of air resistance, gravity on the Earth pulls objects that are in projectile motion downward with an acceleration of 9.8 meters per second squared. 9.8 meters per second squared. Just as it pulls down all falling objects. So orbiting is a projectile motion. And you can see, eventually, going over and down and over and down and over and down, eventually the ball is going to hit the ground. And then, of course, friction will slow it down very quickly. Although air resistance does cause some drag as you throw it, at least when we're talking real-world events. So as little air resistance as possible, and it will pretty much maintain a constant horizontal velocity and a constant downward acceleration. And I believe that's where we're ending. So, oh, there is a picture also. So make sure that you check out the picture of the orbiting space shuttle, which you should be able to see right in your notes. And stay tuned for the last section of Chapter 12, which you guys will be able to watch starting tomorrow night, Wednesday. Have a good night.